Shift Commander. Okay, we are recording our video. Let's start.
Okay, let's start.
Yeah.
Okay, nice to see you.
Okay, nice. Okay, and we in the last part of our video we divided our the content or the subtopics, and we divided and the literary review on the topic. I'm starting at this topic, and Madyiar continuing, and we doing it. Okay, let's start. For the first is a literary review on the topic, and I write it like the intro, and I refer to the other works. It's mostly the articles and the books, and I have a few about the in the internet resources. Okay, for us, given the task where we must research and investigate the process of excitation of a hydrogen atom based on the effective potential. First, we denote the hour of effective potential and rewrite them to introduce them. Okay, firstly is our effective potential and the A and the B coefficients, and for the calculation we dimensionalize them. Firstly, the effective potential takes into account the quantum mechanical diffraction effect in small distances and the effect of the screening in large distance, and have the definite values in the distance that approximately equal to 0. The developer of this effective potential, our national scientists, and in the University Kaznu, and the Shanelov, Jumagulova, Ramazanov, and Jumagulov. The theoretical research and the computer modeling of properties of plasma represents as complicated problem that requires non-trivial solution. How we know? We have the moderate densities, and we need to consider collective interaction of particles in big distances that goes to screen effects. The atom collisions in the hot dense plasma, it is an interesting question in last decade. And the main interest of this event, the problems spectroscopy of this like plasma, and also the process to relate to electron-like heat-like excitation, ionization, and the recombination. And for the first to describe and investigate about the excitation, we discuss about how we solving the wave function. And the Madyiar continuing, please.
Yes, so in this part of our work, there is a given analytical derivation of the wave functions for radial and spherical parts, and the main goal of this part is to give some solutions and derivation of formulas. So we have first of all the stationary wave equation, like it in formula number 1, where nabla squared is a Laplace operator in spherical coordinates, and as we see, the last part of this expression distinguishes from others, and it differs from others because one of the function don't depend on phi, and so we consider it third formula like it's written below. So where the coefficients A and B taken like this. So for the solution of equation, we use the method of separation of variables in the wave function. That's way we have V that depends only on R. Wave equation we can separate for 2 equations, and one of them have considered the variable R, and second of them only the variable theta. So to do this equation, we write the formula like it's written in 6, and we put this in the last equation 6 6 into 4, and result is written like this. So and now we can note we know that in last equation in the left side of our equation it depends only on r, and the right hand side on the right hand side of this equation it depends only on theta, and that's way with the both sides are equal in any values of theta and r. So the both sides equals to the sum constant, and that we can denote as L plus 1. So as we see, the equation 9 represents itself as a particular case in equation of Lagrange. So because this equation of it's second order, that's why it's have two linear independent solutions, and both of them we can represent as power of a series from cosine. Cosine theta. So the both solutions goes to the infinity when theta is equal to 0, and if L is not equal to 0 or to some positive integer. So that's why the acceptable solution in physical point view of wave function are satisfying when L is equal to 1, 2, or 2, I mean, no, 0, 1, 2, and so on. And so soon we see L serves as measure of momentum of bombarding particles that relates to motionless center of scattering, and that's why L is called the quantum number of momentum. And first possible solutions are showed and written below, where the function p, p1 cosinus theta presents as well-known polynomials of Lagrange.
Okay.
So that's the end of second part.
Okay, thank you, Madyiar. And for the third part is a demonstration of analytical methods for obtaining the differential excitation cross-section by phase shift. Method of partial wave was proposed by the Faxenom and the Hosmer Markham that is similar to developed Rayleigh in classical theory of scattering. The initial point in Schrödinger equation for particles that scatters is some central pole with potential. How the Madyiar said, we denote this potential, and we add our effective potential and obtain this formula whether we denoted in the previous AB coefficients. And the solution of this equation is represented as the 11th formula, and for the center of symmetric field scattering amplitude is represented as a at this formula whether we integrate them, that in large distance describes the falling flat surface that's spreading along z-axis and the divergent spherical wave. In these equations, the K model of wave vector of scattering particle and the V is the angle between the direction of scattered and the falling wave. Magnitude of function that depends on the V angle that have the distance that obtain the naive amplitude of scattering, and the differential cross section of scattering is equal to this formula where our function V is in the square and the d omega. And by this, the solution of the Schrödinger equation allows definite magnitude that describes the effect of scattering that called phase scattering or the phase shift. For the fourth topic, I choose it because the differential cross section is strongly relates to the fourth topic. It's a study of the differential excitation cross section and the graph or plot by phase shift method After the obtaining the differential cross-section formula that write it in the last equation exists. And we must denote our values or magnitudes. Firstly, we take our last function and dimensionalize them, and we insert the dimensionless parameters. The dimensionless parameters is a rs equal to the 7, and the gamma is equal, or the coupling parameter is equal to the 0.7, and we have the constant of the Boltzmann that equal to the 0.8 multiplied by the AB Bohr A power of the -1. And after that, we calculate the values of the differential cross-section that is the sigma divided by the d omega with dependence of the scattering angle. It means that we do the loop by our programming language, and after we obtain this table 1, this loop is it starts with the 0 of the scattering angle and it ends in the 180. And by this case, we obtain these values. After this table shows the values of the differential cross-section with dependence of scattering angle theta. After the obtaining table 1, we can plot the graph by these values, and we obtain our plot. This plot describes the dependence of the differential cross-section and the scattering angle. By this plot, we can conclude that differential cross-section strongly depends on the parameter of density and the coupling parameter, and also the Boltzmann constant. With the increase of the energy heating electron, differential cross-section of scattering are decreasing faster with fixed coupling parameter and the density parameter. Okay, and continue, Madyiar.
Okay, so the fifth part, it is a demonstration of ways to obtain the complete excitation cross sections analytically by phase shift method. So after obtaining the differential cross section of excitation, we can go over from Schrödinger equation to equation for phase scattering or phase shift. So the equation for obtaining phase function that looks like this one. Insert formulas where the GL and NL is Riccati-Basele's functions, and the phase shift are located from the solution of equation 13 for big distances. So this equation was firstly obtained by Dukarov, Kinch, Olson, and Calogero, and in the expression 14, amplitude of scattering are located by the phase shift on the infinite removal of particles from each other, as the formula which is written in 15th, where P by cosinus theta are the polynomial of Lagrange, as it's shown in second part. So it is a polynomial Lagrange of L's order, and lambda I, it is the phase shift in infinite. So we should note that equation of that phase scattering as equivalent to Schrödinger equation, but phase shifts have advantages. The main advantage of this method is that the solution phase shift is difficult, but more easier than Schrödinger equation. So we can use the effective potential as always for our task. So yes, you can go down. So the exchange of energy with hovering with energy E and atomic electrons accounted for based on energy conservation laws and momentum, which leads to dependency of transmitted energy and angle of scattering, like it's shown in 17th formula. The differential cross-section that we have obtained was used to calculation excitation cross-section. So with lower limit integration by angles of scattering was changed by minimal angle that defined by 17th formula expression that goes to this formula in 18 years.
Okay, good. Thank you. And for the
yes.
yeah.
Okay. So in sixth part, it is a study and a graph or a complete excitation section. This parameters that we have used is gamma is 0.0 and RS equal to 2. And for the plotting the complete excitation, we firstly calculated the values of complete excitation cross-section, and to obtain the values we use the 18th formula, and to calculate we obtain the differential cross-section values by the effective potential, and after we calculated the complete excitation cross-section. And additionally we for calculation we obviously dimensionalized our equation, and after dimensionalizing we insert dimensional parameters, and as I said, R is equal to 2 and the gamma is equal to 0.0. And after the calculation, we obtain the values, we construct, and where the total excitation cross-section depends on this lambda excitation, and that depends on energy. It means it's like cross-section depends on energy. So as it's shown in the table 2, and the table describes the dependence of total excitation cross-section that depends on energy, and energy values from 0 to 350, and cross-section values are shown in the right-hand side of this table, so we can plot the graph.
Okay.
So this graph describes the dependency of excitation cross-section on energy, and as we can see, with the growth of energy, firstly cross-section also grows, and after reaching the some point it goes down. So yes, and after analyzing the graph, we can say that excitation cross-section increasingly with decreasing of parameter R, and the decreasing of coupling parameter gamma, and this analysis depends on the effect of correlation effects on field shielding.
Okay. Thank you, Madyiar. And for my last topic is a comparison of the result with other experimental theoretical work. For the comparison of result with other experimental theoretical work, we take into account the work of the research of process of excitation of internal state of the hydrogen atom that written by the Shalenov and the Jumagulova, Ramazanov and Jumagulov. To compare the works of investigation of the excitation of the internal state of hydrogen atom, we take into account the graphs that we plotted in fourth and the sixth chapter, and take into account differential cross-section and the excitation or total cross-section in the work. In the first chapter, we derived the plot that describes the differential cross-section and compare with the plot where is described the differential cross-sections that derived in the work of investigation of internal states of a hydrogen atom. For this case, and we after the comparison, we can see that we have the small difference in very small values with graph of differential differential excitation cross section in this work. The errors is occurs because occurred from the taking big steps in calculation for us calculation, but in the work they use the small steps, and we for the integration method use the rectangular integration method. In 6th chapter, we obtain the excitation cross section and the weak comparison with the total cross section, and then we have these plots. In the left hand side, we have our derived cross section plot, and the right hand side we have the depends the comparison of total cross section obtained from the calculation with parameters rs2 and the gamma equal to the 7 in the compared work. We can observe that the graph we have obtained differs in very small values with the graph that obtained by Shalenov, Zhumagulov, Ramazanov, Zhumagulov. By analyzing the graphs, we can see that the total excitation cross section decreases with increasing gamma or coupling parameter. The reason for this and the other phenomena are the de Broglie wavelengths and the Debye radius that includes wave particle nature of the observed particles. Okay, and for last.
So, okay, let me conclude this work, and in the basis of effective potential of interaction of particles in non-ideal quasi-classical plasma, which account effect of screening of charged particle pole in big distances, and diffraction effect in small distances was researched in excitation of hydrogen atom, and our obtained work have good result in comparison with other works.
Okay, thank you, Madyiar, and we have the reference, and we add the link for these videos, and